In this ICFD++ example, we are going to demonstrate Magnus force computations for rotationally symmetric and non-symmetric projectiles using the new Integral Computational Multiphysics Advanced User Interface, or ICMP AUI. Before diving into this example, I will briefly cover the new features and components of the ICFD++ AUI for the first-time user. For a more in-depth understanding of the ICMP AUI features common across all Metacon software, please click on the ICMP AUI demo link popping up on the left side of the video, or refer to the ICMP AUI section of your ICFD++ documentation. This ICFD++ interface is composed of the menu bar, where the mouse is currently moving, the toolbar, which has the shortcuts to commonly used functions and visualization controls, the canvas, in which the geometry or solution is displayed, and the notebook, currently showing that you're in the CFD++ simulation setup mode. Within the notebook, ICFD++ has its action tree or setup wizard, which will guide you logically through the various steps of the problem setup, and one or more information trees, in this case, the groups and boundary families tree and boundary conditions tree. Corresponding to each action item in the action tree or information tree is its action panel, where the user is given the relevant choices based upon choices made in previous and current panels. All panels are dockable and resizable. Now I will go into some background and the problem definition for this example case. A projectile traveling in a fluid experiences forces and moments, most commonly lift, drag, and pitching moment. In addition to these, if the projectile is spinning, a lateral force and a yaw moment also act on the projectile. Due to its spinning motion, the projectile accelerates the fluid on one side and decelerates the fluid on the opposite side. This results in a pressure difference in the laterally opposite sides of the projectile, which ultimately results in a lateral force and a yaw moment, which are known as the Magnus force and Magnus moment respectively. This example demonstrates how CFD++ can be used to calculate the Magnus force and moment for rotationally symmetric and non-symmetric projectiles. For the case of a symmetric projectile, we have air coming in at Mach 1.5 at an altitude of 0 kilometers and an angle of attack of 5 degrees. Since this projectile is symmetric, we can apply an axial wall rotation boundary condition of approximately 650 radians per second. To solve this problem in ICFD++, we will be using the aerodynamic wizard, which will set up everything we need for the simulation except for the boundary conditions, a wall rotation boundary condition, and since this example will be a rotationally symmetric object, we can run this in a steady state mode and get a steady state solution. For the case of a non-symmetric projectile, we will have air coming in at Mach 1.5 at an altitude of 0.0 kilometers and an angle of attack of 5 degrees. As a result of fins being present on this projectile, we can no longer use a wall rotation boundary condition. Instead, we will need to physically rotate the grid at 650 radians per second and run a time-accurate simulation. For the non-symmetric projectile case, we'll once again be using the aerodynamic wizard to set up the problem except for the boundary conditions and also the grid motion in this case. We will initially run a steady-state computation without the grid rotation in order to establish the flow. Subsequently, we will do a transient time-accurate restart with the grid rotation turned on. Once the ICFD++ AUI has been brought up, the initial action item in the action tree will be to specify a working directory. By default, the current working directory has already been entered into the working directory field. If needed, the users can browse for a different working directory. We will go ahead and press OK at the bottom of this action panel to proceed to the next action item. The next action item in the action tree will be to load the input and grid files. In this case, we will go ahead and say yes to analyzing the grid files. As well, we will say yes to loading in the BC family file. At the bottom of this action panel, proceed to press OK to accept these items and move on to the next action item. The grid analysis has been performed, and information about the grid will be shown in the grid information panel. Go ahead and press OK at the bottom of this panel. You will then be led to the next action item, which is the cell types and volumes action item. The action panel for this has already been populated with information from the grid analysis. In this case, we have a 3D grid with triangular prisms and tetrahedral and pyramid cell elements. We'll go ahead and press OK at the bottom of this action panel to proceed. Next, we're prompted with the action item to specify the problem definition. In this case, we are solving a general fluids problem, but we will be using a problem class wizard to specify the settings for us, and in this case we will be using the external arrow aerodynamics wizard. Once we have that set, we will go ahead and press OK at the bottom of the action panel to proceed. Next, we are prompted with the external arrow aerospace wizard action item. In this action panel, we can specify the problem definition of the incoming flow. We will choose to run this case in dimensional SI units. We will specify Mach number and altitude. For the free stream Mach number, we will enter 1.5. For the altitude, we will enter 0. We will keep a delta temperature of 0.0. The wizard will automatically determine the atmospheric temperature. The angle of attack will be in the XZ plane, which we'll keep from the default setting. And we will enter an angle of attack of 5.0 degrees. We will keep the default yaw angle of 0.0 degrees. We will also keep the default settings for turbulence intensity and the turbulent laminar viscosity ratio. There is a button at the bottom that tells you what the computed temperature is at this altitude. If you hit show temperature, it will show you that at this altitude the temperature is 288.15 Kelvin. We'll go ahead and press OK at the bottom of this panel. At the bottom of the Aerospace Wizard action panel, you'll see a button to expand, and this will show you the steps that the wizard will take to set up the problem. In this case, it will specify an equation set type of compressible perfect gas, Navier-Stokes Euler. It will initialize the domain with the quantities specified in this action panel. It will also compute the turbulence values, the K and epsilon values, based on our entries. It will set air as the working gas, and also set the time integration quantities. We can go ahead and press OK at the bottom of this action panel to accept these settings and proceed. Once the wizard has completed its setup, a panel will be prompted letting you know of its completion. We will go ahead and press OK to close this panel. Although the wizard has completed the majority of steps in the problem setup, we still need to specify the boundary conditions for this example. So if we scroll up on the action tree, we'll notice that the boundary conditions action item has not been completed. It's been marked with a red X. We will go ahead and highlight this using the left mouse button, opening up the boundary conditions action panel. Now, if we take a look at the canvas section of the AUI, I want to go over a few mouse controls to visualize the grid. Using the left mouse button, holding it down, we can rotate the grid around the cursor. Using the middle mouse button, we can translate the grid. And using the right mouse button, moving it up and down, we can zoom in and out. Now, if we go to the boundary families tree in the notebook, we can use some of the items here to hide or show the wireframe grid. We can click on the item to the right of the wireframe option to shade the grid. We can also turn off the wireframe option to just see the grid shaded. We can highlight the grid by hitting the left mouse button on a particular boundary family. And we can also hide the grid by hitting the middle mouse button on the boundary family. And we can redisplay it by hitting the middle mouse button again. Moving back to the boundary conditions action panel, we will proceed to applying the boundary conditions for our boundary families. We can first highlight the first boundary family, the outer boundary, by single mouse clicking the left mouse button. Now we want to apply a open boundary condition to this outer boundary family. After highlighting the boundary family, we're going to hold down the left mouse button and drag it over to the open boundary condition subtype. Releasing the left mouse button will place this boundary family into this boundary condition subtype. A panel will be prompted where we can specify the open boundary type for this boundary family. We will keep the default inflow and outflow subgroup. We will specify the primitive variables. And for the actual boundary condition type, we will apply a characteristics-based inflow-outflow boundary condition. We already have information set created by the arrow wizard, one we've already used for the initial conditions. We will go ahead and use the same information set for this outer boundary. You'll see that the arrow wizard, based on our inputs, has already determined the pressure, which is 1 atmosphere, the temperature, and the velocity components, which already takes into account the 5-degree angle of attack, and it already has the turbulence quantities specified as well. Once we have this applied, we can go ahead and press OK at the bottom of this panel to accept these settings. Next, we will go ahead and apply a wall boundary condition to boundary families 2, 3, 4, and 5, which constitute the boundary families of the projectile. With a single mouse click, we can highlight boundary family number 2. Then holding down the control button, we will proceed with the single mouse click to highlight 3, 4, and 5. After these boundary families have been highlighted, we will hold down the left mouse button and drag and drop to the wall boundary conditions subtype, releasing the left mouse button. A panel will be prompted with specifications for the wall boundary condition. We will keep the wall type as viscous. We will set the wall integration to wall function. We will keep the heat transfer to adiabatic. But the wall motion type for this particular example, we will set to be a rotational wall motion. The axis of rotation we will keep as the x-axis. Now for the specification of the rotational speed, we will create a new information set. So we will hit the plus button, creating a new information set. We will highlight this and check it. The rotation rate we're going to set as 650 radians per second. The center of rotation, the Y center and Z center, we will keep at the default 0 values for both. We will not apply a rough wall modifier or any of the other modifiers. Once this has been set, go ahead and say OK at the bottom of this panel to accept these settings and proceed. Now that we have all of the boundary families set, we can go over to the boundary families tree in the notebook, and if you move your mouse cursor over each respective family, you will see the boundary condition applied to them. Once we've set this, we can go ahead and press OK at the bottom of the boundary conditions action panel to close this action panel. We are then automatically brought to the turbulence control action item in action panel. The reason we are is because we've specified a wall function wall BC, and as such the wall function settings are found in this control panel. We will accept the default settings for the wall function and press OK at the bottom of this action panel to proceed. Now we're ready to save the input file and run the computation. We've kept the check mark for save the input file, and we've added a check mark for the run CFD++ option. We will go ahead and run this in double precision mode and as a single CPU computation. The solution files will be written to the current working directory. For information on post-processing, please refer to the post-processing section of this example case. Now I'll proceed to do the setup for the rotationally non-symmetric projectile case. In part 2 of our example, we will go over how to set up a simulation that demonstrates the Magnus force and moment calculations for a non-symmetric projectile. This example will be done in 2 steps. In the first step, we will run a steady state computation without any grid motion. In the second step, we will restart a transient computation from our steady solution, this time adding grid motion. A lot of our steps in this example will be very similar to part 1. As a result, I will not spend too much time going over the details of items that are very similar. If you want more details, please refer to part 1 of this example. Once the ICFD++ AUI is brought up, we are first asked to identify the location of the working directory. In this case, we've opened the AUI in the working directory, so the location has been automatically entered into the working directory field. If you need to, you can enter the Browse option to browse for a new working directory. We can go ahead and press OK at the bottom of this action panel to accept this working directory and proceed down the action tree. We are then taken to the Load Input Grid Info action item. Here we're asked whether or not we want to analyze the grid and load the BC family file. Once the grid analysis has been performed, we are given the grid information in a new pop-up panel. Here we are told the number of cells and the cell type in the grid, as well as the number of BC families and external BC family faces for each BC family. We can press OK at the bottom of this panel to close it and proceed. Next, we're automatically taken to the Cell Types and Volumes action item. Once again, as a result of the grid analysis, this action panel has already been populated for us with information regarding the grid. We can proceed by pressing OK at the bottom of this action panel. Next, we are going to define the general problem definition for this computation. As with part 1, we will proceed to use a wizard to set up the majority of our computation. The wizard we will be using, just as with part 1, will be the external arrow wizard. Once we have this selected, go ahead and press OK at the bottom of the action panel. In the external arrow wizard action panel, we will set the dimensional units to be SI. We will use Mach number and altitude for our inputs. For the free stream Mach number, we will enter 1.5. We will keep the delta temperature to be 0. This means that we will accept the temperature calculated for the altitude we've prescribed. We will enter the angle of attack of the incoming flow to be in the XZ plane. The angle of attack for this computation will be 5.0 degrees. We will not have a yaw, so we will keep that value to be 0. We'll keep the default values for turbulence intensity and turbulent laminar viscosity ratio, which will be used for the initialization of our turbulence quantities, K and epsilon. By clicking on Show Temperature, we'll see what the computed temperature is at this altitude. For the altitude we've entered, it will be 288.15 Kelvin. Go ahead and press OK at this pop-up panel to close it. If you expand the Show Steps option at the bottom of the AeroWizard action panel, you'll see the steps that the AeroWizard will take to set up this computation. We will press OK at the bottom of this action panel to accept these settings. We are then given a panel telling us that the AeroWizard has completed its setup. Go ahead and press OK to close this. Now the AeroWizard has gone ahead and done the majority of the setup for us. The only thing left to do is to assign boundary conditions to our boundary families. We can scroll up the action tree, and we'll notice that the boundary conditions action item has been left incomplete. We'll go ahead and highlight this action item by single left mouse clicking. This will bring up the boundary conditions action panel. Here we'll proceed to apply boundary conditions to our boundary families. Just as with part 1, we can highlight the outer boundary family, BC number 1, with a single left mouse click, and we will drag it over by holding down the left mouse button to the open boundary condition type, letting go to apply it to that open boundary condition. This boundary condition will be the same as it was in part 1. The boundary condition subgroup will be inflow and outflow. The type of information will be primitive variables, and the applied condition type will be characteristics based. In terms of the information at this boundary, we will choose to use one of the information sets created by the AeroWizard, which has been used for the initialization of the domain. We will highlight this information set as well as check the circle next to it. And we can go ahead and accept these settings by pressing OK at the bottom of this panel. Next, we will go ahead and apply boundary conditions to boundary families 2 through 7. These boundary families will all have the same boundary condition. Let's start by highlighting boundary family number 2, the body, with a single left mouse click. Then we can hold down the control button and select each of the other boundary families all the way up to BC7 with single left mouse clicks. Now, holding down the left mouse button, we will go ahead and drag all of these over to the wall boundary condition type and letting go to have them applied to this boundary condition type. This will bring up the wall boundary condition information panel. Just as with part 1 of this example, all of these walls will be viscous walls. The wall integration will be wall function. The wall heat transfer type will remain adiabatic. But unlike part 1, we will not be applying a wall rotation to these walls. We will leave the option to be stationary with respect to mesh motion. We can press OK at the bottom of this panel to accept these settings and proceed. You will now notice that the boundary family tree in the notebook now has check marks next to each of the boundary families. This indicates that a boundary condition has been applied to each of them. If you move the mouse cursor over each of these boundary families, you'll notice that you'll get information regarding the boundary condition that has been applied to them. We can go ahead and press OK at the bottom of the boundary conditions action panel to proceed. We are then taken to the turbulence control action item. We will accept the default settings in this action panel. We can go ahead and press OK at the bottom to accept and proceed. Next, we're taken to the Save and Run action item, where we can save the input file and run the computation. We will do so in double precision, and we will run it with a single CPU. You can press OK at the bottom of this action panel to commence with the computation. Once the steady-state computation has completed, we can proceed with setting up the transient restart. The first step in this setup will require us to go to the CFD problem definition action item in the action tree. In the action panel for this item, we will go to where it says nature of simulation, simulation type, and we will change it from steady state to transient. Once this change has been made, we will proceed by pressing OK at the bottom of this action panel. This will take us to the equation properties action item. We'll keep the same equation properties as we've had before. It'll be a RANS computation where we use the two equation realizable k epsilon. Both of these settings were set for us by the arrow wizard. We can accept these settings by pressing OK at the bottom of the action panel. We will then be taken to the fluid properties action item. Once again, we can accept the settings prescribed by the arrow wizard by pressing OK at the bottom of the action panel. We will not need the help set numerics wizard to make any changes for us, so we will press OK at the bottom of this action panel. Once again, we will use the settings prescribed by the arrow wizard in the Riemann solver action item. We can go ahead and press OK to proceed. In the simulation strategy action item, we will say yes to the option for is this a restart, since we will be restarting from the previous steady state computation. We will keep the integration type to be implicit. We will run for the default 500 iterations, and we will keep all other options at their default state and press OK at the bottom of the action panel to accept and proceed. We will then be prompted with whether or not we want to load some default settings for the transient mode. We will say no to this option and press OK at the bottom. In the time integration action item, we will set the local coordinate number to be a constant value of 50. For the global time step size, we will enter 4.83 e minus 5 seconds. We will enter the maximum number of internal iterations to be 10. And we will set the internal iteration convergence criteria to be 1 e minus 3. And we will set the order of global time stepping to be second order. Once these settings have been applied, we will press OK to accept and proceed. Go ahead and say OK to the default settings for the spatial discretization action panel, as well as the neutral plot file options panel. Go and say OK to writing to the neutral plot file options input file. Now, before we run the computation, we need to go back and apply a grid motion. This can be done by scrolling up and going to the additional specifications action item. Here we will say yes to the first option, apply grid motion. We'll keep the option for activating 6-DOF based motion, no, and say yes to activating another type of motion. We'll press OK at the bottom of this action panel to accept and proceed. Now I will expand the action panel for the grid motion specification so we can see the entire text of the options. Since we do not have a cell groups file for this grid, we will apply the grid motion to all groups, which includes all cells in the grid. We can highlight the all groups using a left mouse click, and then we will hold down the left mouse button to drag and drop this to the analytic translation or rotation velocity option in the grid motion type tree. This will bring up an information panel for this grid motion type. We will select a x-axis rotation. The rotation rate we will enter as 650 radians per second. And we will keep the y and z centers to be 0 and press OK at the bottom of this panel. Once this has been applied, we will press OK at the bottom of this action panel to proceed. We will keep the default options in the overall grid motion control panel and press OK at the bottom. Now we are ready to run the computation. We will proceed to save the input file and check the Run CFD++ option. We will go ahead and run this in double precision and use a single CPU for the computation. We can press OK at the bottom of this action panel to commence with the computation. For information about post-processing, please refer to the results section of this example. Thank you.